Hello, thank you for taking the time to attend this presentation. My name is Kyung Kim, and today I will present our research on embedding and detecting watermarks in LLM-generated text. This study addresses one of the pressing challenges posed by the rapid advancements in large language models, and we will present our motivation, methodology, results, and contributions. In recent years, we have witnessed the unprecedented growth and widespread adoption of large language models such as ChatGPT, Llama, and GPT-4. These models are capable of generating text that closely mimics human writing, making it increasingly difficult to distinguish between human and AI-generated content. While this innovation has driven advancements in numerous domains, it has also introduced significant risks. The potential misuse of these models for spreading misinformation, plagiarism, and evading accountability is a growing concern. The need for a robust mechanism to claim ownership of an AI-generated text and ensure traceability is paramount. To address these challenges, our study explores the embedding of watermarks into LLM-generated text as a means to enhance transparency and accountability. This page is about the related work in the domain of watermarking techniques for text. The approaches can be broadly categorized into two sections: watermarking for existing text and watermarking for LLMs. On the left, these are watermarking for existing text. Format-based watermarking method is embedding hidden patterns by altering text layout features such as line spacing or adding invisible symbols. While it does not affect readability, it is easy to detect and remove. Second is lexical-based watermarking. This method is to replace synonyms. For example, substituting happy with joyful. Although this preserves the semantic meaning of the text, it is limited by vocabulary constraints. Synthetic-based watermarking method modifies grammatical structures, such as converting active voice to passive voice. Generation-based watermarking integrates watermarks during the text generation process itself, leading to seamless and natural watermark incorporation. On the right, these are watermarking techniques specifically designed for LLMs. Logic generation embeds watermarks directly in the probability distributions produced by the LLM. Token sampling selects specific tokens during the generation process to ensure watermark presence. LLM training incorporates watermarks during model training, ensuring that all outputs inherently contain the watermarks. Our proposed framework builds upon these methods while addressing their limitations. Our study is guided by two fundamental research questions. First is, how can we embed a watermark in LLM-generated text while maintaining natural text quality and creating traceable patterns? To address this, we utilize context-aware modifications such as replacing words with synonyms that preserve semantic integrity. Additionally, statistical patterns like those based on z-scores ensure the embedded watermarks are traceable. Second is, which method provides the most effective detection and retention of watermarks? Through our analysis, we found that Z-score based detection is the most robust approach, providing high accuracy and resilience against text modifications, while threshold-based methods are simpler and more efficient. They lack robustness. Probabilistic insertion methods add unpredictability but may compromise detection reliability. A hybrid approach that combines these methods is recommended to maximize their strengths. Next, Byung-Yun will present from the methodology of our algorithm to the conclusion of our research.
Our methodology comprises three key components which collectively ensure a robust watermarking process. First step is word-based binary encoding. Each word in the text is converted into a binary value using the SHA-256 hash function. This deterministic process ensures consistent and reproducible patterns, forming the basis for traceable watermarking. Second step is candidate word generation using BERT. To replace words while maintaining semantic meaning, we employ a masked language model based on BERT. Target words in the input text are masked, and BERT predicts contextually appropriate replacement. Among the predictions, the candidate with the highest semantic similarity to the original word is selected. Third step is detection algorithm. The detection process involves analyzing the binary encoded values in the watermark text. Using statistical Z-score validation, sentences with Z bigger 1.96 are identified as successfully watermarked with 95% confidence. This ensures reliable detection even under adversarial conditions such as text paragraphing or minor edits. Our experimental evaluation leverages the human ChatGPT comparison corpus, a comprehensive dataset designed to compare human-written and AI-generated text. The dataset contains over 48,000 samples, each comprising a user-provided question, human-written answers, and ChatGPT-generated responses. For our study, we specifically focused on 50 ChatGPT-generated sentences from the ChatGPT answers column. These sentences were used to evaluate both the watermark injection and detection processes. The experimental setup consisted of two main stages. For watermark injection, we applied our BERT-based watermarking framework to replace words in 50 sentences from the HEC3 dataset. This ensured that the watermark text retained its original semantic meaning. For watermark detection, to evaluate the effectiveness of our detection method, we applied Z-score validation. Sentences with Z is bigger 1.96 were classified as successfully watermarked. Out of 50 sentences, 44 were successfully detected, achieving an 88% success rate. This demonstrates the robustness of our approach. However, 6 sentences fell below the detection threshold. Our study contributes significantly to the field of LLM watermarking through a well-rounded framework. First, we introduce context-aware watermark embedding, which utilize BERT-based masked language modeling to replace words with contextually appropriate synonyms. This approach ensures both grammatical accuracy and semantic integrity, supported by part-of-speech filtering. Next, for deterministic binary encoding, Our framework leverages SHA-256 hashing to generate consistent and traceable patterns, providing a strong foundation for watermarking. Finally, we employ robust statistical detection using Z-score-based analysis, which ensures high accuracy and resilience against text modifications like paraphrasing. By integrating these methods, our framework achieves a balance of efficiency, robustness, and natural text quality, making it a practical solution for watermarking LLM-generated content. In conclusion, this study introduces a robust framework for embedding and detecting watermarks in LLM-generated text, balancing natural text quality, robustness, and detection accuracy. Using BERT-based masked language modeling, we ensure contextually appropriate synonym replacement while maintaining grammatical coherence. A deterministic binary encoding function based on SHA-256 hashing creates traceable patterns, and Z-score-based detection ensures high accuracy and resilience to adversarial modifications like paraphrasing. Despite limitations such as this dependence on BERT, vulnerability to adversarial attacks, and computational costs, this framework lays a strong foundation for advancing watermarking technique in AI-generated content. We have explained LLM-based to text watermarking. I hope this presentation has been helpful for your research and practical applications. That concludes our presentation. Thank you for listening.